This is a continuation of my discussion on atomic radii, but I've actually went to my periodic table and I've got a couple of different atoms here that we're going to talk about the sizes of these. So if I take these, and I want to do these in pairs and maybe threes here in just a moment, because that's the kind of thing that we might potentially see with regard to an essay or a multiple choice question. So I'm going to start here with lithium. And if I wanted to make a prediction about the atomic radius of lithium compared to beryllium, first off, I'm going to predict that lithium is larger than beryllium. And this is a continuation of my previous video, because we learn that beryllium is going to be smaller because they have essentially the same shielding effect, same number of layers of electrons, 2 layers, series 2, but beryllium has a more effective nuclear charge. On the other hand, if I want to make a prediction here between lithium and sodium, I'm going to predict that sodium is larger than lithium. Draw that way. I hope that's not too confusing. Sodium is larger because sodium has another layer of electrons. Sodium has a greater amount of shielding. And I'm not really going to use the words effective nuclear charge there, because if I do, I have to use it to almost define what shielding is. I have to say, well, sodium has a more effective nuclear charge, but because it has a more effective nuclear charge, it draws its closer layer of electrons, its first and second principal energy level electrons, in closer, therefore blocking or shielding the forces on that outer electron, and thereby making its atomic radius larger. Again, I want to keep that as short and simple as possible. I'm just going to say sodium is the largest of those three because sodium has more shielding than lithium. Lithium's bigger than beryllium because lithium has a less effective nuclear charge. And then I would predict the same thing down here to potassium. Potassium is the largest of all 4 of those because it has the greatest amount of shielding. Going back up here and picking up, I would say beryllium is bigger than boron, because as I go across through here, I'm in the same row, essentially the same shielding, but I'm getting a more effective nuclear charge, which is going to make these atoms smaller. Again, that's me making predictions. There may be some exceptions to that, and if we get into those, we probably will, because almost inevitably you'll find an exception. I'll mention it if that's not really the focus of why you're here watching this video, to try to explain anomalies. Normally the anomalies come along when you start learning about modern quantum mechanics and orbital notations and electron configurations. I'm kind of gearing this more as an earlier lecture. So oxygen is the smallest of all of those across the top, and actually of all of them that I have done so far. Now, compared to oxygen, sulfur is bigger, more shielding in sulfur. Selenium is the biggest because it has more shielding than sulfur or oxygen. So let's see how we did. I've got a periodic table here that happens to have an atomic radius in picometers, third number down. So I'm going to go here and I'm going to actually write these numbers in beside each one. Lithium is 156. Beryllium is 111. I got one right so far. Boron is 97. I'm on a roll. Carbon is 77. Nitrogen 55. And oxygen, when I get to it, ends up being 60. So, oops, I missed that one in my prediction. Again, depends on the intent of why you're watching this video. I'll explain here in just a moment, why that happened. But nonetheless, we're making predictions, and we're trying to justify our predictions. Now, the reason for this, if we're going to encounter anomalies, there's a couple of things we run into. One is called sublevel shielding, and I do some lectures on photoelectron spectroscopy and sublevel shielding and talk about ionization energies and that stuff. Normally what we'll see is an anomaly as we go maybe from here over to here, like from beryllium to boron, as we jump from this part to this part on the periodic table. That's a place where it will occur from time to time. That normally has something to do with sublevel shielding. We were all right there. And then the other thing that I will encounter sometimes happens, it can happen between these two here. Again, you got to have a little understanding for electron configuration, orbital diagrams to know how this works, but I'll just go over it briefly. And the other place that it happens is right here in the middle. So in the middles, or as we jump from a block to a block. If it happens in the middle, and that's what happens here, what we get into is, if you understand orbital diagrams and electron configuration, nitrogen is a 1s2, 2s2, 2p3. So in terms of an orbital diagram, it's something like this, one in each orbital. Again, if this is above you, just fast forward through this part. And so anyhow, what happens when we move on to oxygen is we end up with this. And so we get something occasionally known as two electrons in the same orbital, and we get what's called electron-electron repulsion. So that'll occasionally explain some of those anomalies. As I move down to sodium, I've got a 186, so we're good there. And on down to potassium, 231. Sulfur, 104, and selenium, 115. So again, all predictions there were pretty good. So other than this one space right here, not too bad with regard to the predictions. Now, we can also do diagonal predictions. I'll do diagonals occasionally, but I like to keep them close, and I only like to do them one way. The reason for that, I might do sodium compared to beryllium. That diagonal is not bad as you go kind of upright. And the reason why, as we go up, they get smaller because of less shielding, and as we go right, they get smaller because of a more effective nuclear charge. Ultimately, which one is the bigger factor as to why sodium is the largest of these three? It's because of the greater amount of shielding. Now, diagonals the other way is where we occasionally get into some trouble. You know, if we take a look, you know, here's sulfur, and here is beryllium. And what we find is sulfur is smaller. And it's not that we can't do that. It's just not what we would predict. And when it's not what we would predict, then that's when we've got to make sure we're using proper vocabulary. Okay, so evidently it's not the greater shielding, because if it were greater shielding, sulfur would be bigger than beryllium. So then, on the other hand, what is going on in sulfur that makes it, in fact, have another layer, but yet be smaller than beryllium? And that's the fact that sulfur's got a more effective nuclear charge. So sometimes diagonals this way end up doing something like this, and we have to use the terms effective nuclear charge, depending on what you're looking for. We made predictions, we only missed one. We talked a little here about orbital issues with electron-electron repulsion. Diagonals this way, not too bad. But diagonals back the other way, that's where maybe we have to say something like, well, selenium is 115, you know, lithium is 156. Selenium has way more shielding, but it also has a more effective nuclear charge. Which one justifies why selenium is smaller than lithium? Well, it's not shielding, because that would make it larger. Not shielding, it's effective nuclear charge. Good luck with your essays.